Welcome everybody to today's webinar. Our presenter today is going to be Hei-Su Chang, and she's going to talk about induced fit posing in Orion. If there are any questions during the webinar, please post them in the Q&A box on the top right-hand side of your screen. We'll answer those questions towards the end or by email if we don't get to them. Without further ado, please, Hei-Su, yours.
Thanks, Gunther. There are two separable post-prediction problems in the early stage of drug discovery. One can be found in lead optimization. In lead optimization, a congeneric series of a lead compound is designed and evaluated. And here's one example of congeneric series. This is a congeneric series of CDK2 inhibitors. They share a common substructure, which is shown in the box on the left, with varying R groups in the meta and para position of the benzene ring. And this is the latest validation results of POSIT. POSIT is OpenEye's fast molecular post-prediction tool. This plot shows the accuracy of predicting the right binding mode with respect to the similarity of your molecule to the template ligand. The black accuracy curve shows that the accuracy of POSIT is high when your molecule to pose is similar to the template ligand, and the accuracy decreases as the similarity decreases. And the histogram shows the distribution of similarities between the cognate ligands of cross-docking pairs from the validation set. Going back to the congeneric series of CDK2 inhibitors, if one wants to find the binding mode of chemical analogs given the known binding mode of the lead compound, one can use POSIT with high confidence because this post-prediction problem falls into this high similarity area where we have good accuracy of POSIT. But one thing you can notice from this plot on the right is that the majority of cases don't fall into the high similarity area. Where do we encounter cases where the ligand to dock is very dissimilar to the template ligand? In the lead ID stage. In lead ID, hits either from high-throughput screening or virtual screening are evaluated to identify promising lead compounds. And if you know how hits bind to the binding site of your target, it can be a great guidance in figuring out which one should be the lead compounds that we would want to process further. But unlike the congeneric series in lead optimization, hits are chemically very diverse. These are all known binders of CDK2. They bind to the same active site of CDK2, but as you can see from their 2D depictions, they are very different. So if one wants to know the binding mode of the ligands without the luxury of having all of their crystal structures, this post-prediction problem in lead ID now belongs to this low similarity area in this plot where the accuracy of POSIT is below 50%. And this really means that we need another tool which is designed for these cases. Here is one example that shows the case where one needs to consider the active site shape change to correctly predict the binding mode of a ligand. On the right, they are the crystal structures of the first two binders. The ligands are different, so they bind differently, and you can see lysine 33 has different rotamer states in the crystal structures. And let's say we want to predict the binding mode of the yellow ligand, and we only have the crystal structure of the receptor with the blue receptor, a blue ligand bound to start with. Then your post-prediction tool needs to address the reorientation of lysine 33 because it introduced this heavy clash with the correct binding mode of the yellow ligand. And IFP, induced fit posing, is the tool for these cases. It requires two inputs, reference receptor, which is the blue Pac-Man here, and the hit molecule to pose, the yellow block. IFP aims to predict first the right binding mode of the ligand in the reference receptor active site, and second, the right active site shape corresponding to the binding mode. And the protocol of IFP comprises 3 steps. In step 1, you input your reference receptor of interest. Then before docking, it goes through pruning. It takes the active site residues and prunes them into alanine so that it can allow more space in the active site and reduce the chance of losing correct binding pose, which makes heavy clash with the active site residues. Then both pruned and unpruned receptors are used in the docking stage so that it allows a diverse set of binding mode candidates. And after getting docked poses, they are placed back to the original receptor, and since they could have heavy clashes with the protein active site residues, we do a series of minimizations here to resolve the possible clashes. Once the minimization is complete, we do clustering for the deduplication of poses and select top 12 poses to advance into step 2. Step 2 is where we do the actual induced fit using short trajectory MD. Here we are leveraging our expertise in using short trajectory MD to enable the fast and efficient induced fit compared to other programs which OpenTime use much longer equilibration for this stage. Lastly, in step 3, we do scoring to predict which pose would be the most closest one to the actual binding mode. We use the IFP score here, which is the combination of MMPBSA, BinScore, which is OpenEye's knowledge-based scoring function for scoring protein-ligand interactions, and ChemGauss4. Now let's see how this protocol will work for the example case where we need to address the reorientation of lysine 33 to correctly predict the binding mode of the yellow ligand. First, we start with the blue receptor. Then in the pruning stage, we take active site residues including lysine 33 and prune them to alanine. So you can see this is the active site before pruning, and after pruning we have a larger active site for docking. And after docking, followed by a series of minimizations, when we select the top 12 poses, we should have the reasonable binding mode within the top poses, and this is the 1. To measure the success of getting the correct binding mode, the metric we are using is pose-RMSD to the actual crystal structure. The pose-RMSD of this pose is 1.18 angstrom, and you can see here the minimization moved lysine 33 backwards to resolve the clash with the binding mode. And step 2 using STMD indeed relaxes both the binding mode and the active site residues, resulting in better overlap with the actual crystal structure, which is the red structure here. You can see the pose-RMSD drop down to 0.66 angstrom after MD step. And lastly, in step 3, we mark this as the most promising binding mode of the yellow ligand. We conducted validation of IFP on various targets, but before we carried our validation, one question we asked ourselves was, what makes a good validation set? This is one example we encountered at the very beginning of the project. We wanted to see if we could reproduce the binding mode of the yellow crystal structure, but the red structure is what we got from IFP. Pose-RMSD was higher than 2 angstrom, which is the success criteria of this project. And when we looked at the overlap with the actual crystal structure, we could see this fragment of the ligand did not match well with the crystal structure. And this fragment was the high effector area of the ligand crystal structure, which means that the atomic coordinates of the fragment are not well supported by the experimental data. And we do not want to compare our result to the crystal structure, which is not well supported by experimental data like this. So when we curated our validation set, we only chose the cross-docking pairs whose target crystal structure is reliable. And to measure the trustworthiness of crystal structures, we used Iridium, OpenEye's metric to assess the goodness of crystal structures. Iridium takes into many aspects, including electron densities of ligand and active site residues, and we only selected cross-docking pairs whose target crystal structure is highly trustworthy based on Iridium. And with that single criteria, when we looked at the IFDMD paper, they have around 400 cross-docking pairs in their training and test sets, but only 20% of them survived. So we took 69 cross-docking pairs from the paper and we added additional internal 48 cross-docking pairs so that we could include spectrum of properties, including ligand similarity, active site similarity, and the degree of protein-ligand clashes. And let's see some good, bad, and ugly cases from the validation. This is one case study of ALR2 receptor. We wanted to see if we could reproduce the binding mode of the red ligand here when starting from the blue receptor. And you can see the reorientation of Lysine 300 to the left-hand side is required to resolve the clash with the binding mode of the red ligand. Docking from step 1 produces the yellow binding mode with pos-RMSD of 2.8 angstrom. While it places the ligand to the reasonable place, you can see Lysine 300 hasn't been reoriented, resulting in not a good pos-RMSD. But step 2 using short trajectory MD gave enough time for the active site residues, including Lysine 300, to induce fit, reorienting the Lysine 300 to the left-hand side and placing the binding pose to the right spot. And this example shows that MD is a critical part of IFP protocol. Once you run IFP flows successfully in Orion, along with the output dataset, it will provide the summary flow report, where you can find the summary of the top 5 poses, including the IFP scores and the interactions with the active site residues. And at the bottom of the flow report, you will also see the full summary table, where you can find more detailed information about each pose, including a link to the trajectory analysis of the pose. Unfortunately, we had some bad cases. This is one case study of AKT1 receptor. We wanted to see if we could reproduce the binding mode in this red crystal structure, and the yellow binding mode is what we got from IFP. You can see they don't overlap well, and the pos-RMSD was higher than 2 angstrom. We wonder if the bad performance of IFP in this case is associated with the ligand flexibility. This ligand has 11 rotatable bonds, and we want to see if longer equilibration would be necessary for flexible ligands like this. And ugly cases. This is case study of CDK2. We wanted to reproduce the binding mode of a red ligand, starting from the blue receptor, but we failed in predicting the right binding mode of the ligand with pos-RMSD of 6.85 angstrom. But when we looked at the overlap of starting receptor configuration and the target configuration, we could see that Lysine 83 has different backbone configurations between the receptors, indicating that induced fit posing of a ligand which requires backbone configuration rearrangement is the current limitation of IFP that we want to improve in the future. So this is the overall validation result. The success criteria that we used was ligand-heavy atom RMSD within 2 angstrom relative to the actual binding pose. And this bar chart on the right shows the success rate in getting the right binding mode in the top 1, 2, and 5 poses. You can see we have high success rate of 81% in getting the right binding mode in the top 5 poses. And even when we narrow down to the top 1 pose, we still have a success rate higher than 50%. And since we are confident in getting the right binding mode in the top 5, we suggest to carry the top 5 poses either to further examination or to lead optimization. So in conclusion, IFP is a 3-step protocol to predict the binding pose of a ligand which requires induced fit of receptor site side chains. Where it's still under active development, the validation showed a good success rate in getting the correct binding mode in the top 5 poses. And the top 5 poses can be carried forward for further examination or into lead optimization. And these are the list of work in progress. Firstly, we've been working on adding apoprotein support. For now, we only support holoproteins. The cognate ligand in the blue square here is used in finding the active site residues to prune and in the docking process. but the apoprotein support will enable the users to use IFP for their post predictions when they only have an apoprotein to start with. And secondly, we've been studying to see if the enhanced sampling in IFP step 2 will improve the performance of IFP for cases including flexible ligand posing. And lastly, we want to see if the protein enhanced sampling will improve the IFP performance for cases like the ugly case in the previous slide, where it requires protein backbone configuration rearrangement for the post prediction. With that, I'd like to acknowledge all OpenEye colleagues who've been part of this project, especially Suhani and Bing. And I'd like to thank Itai and Maria from Interline Therapeutics. This project started as a collaboration with Interline, and they shared many valuable scientific feedback and ideas throughout the collaboration. And thanks for listening, and now we will have Q&A session.
Welcome back, everybody. Now to the Q&A. Let's see, we have a few questions here. First question, Jesus, it says in step 1 that you described, where the mutated red stored by putting the docked pose back to the original receptor. Have you considered using a sidechain rotamer library when getting the amino acids back?
That's a good question. We haven't used the rotamer sidechain library yet, but yes, that's definitely on our list. So we just started with very simple way, which was putting the binding mode to the original receptor. But yeah, we will definitely gonna try that, and we're expecting to see better sidechain rotamer states to start with the sidechain library.
Okay. I think a related question also around this amino acids, the pruning of the amino acids. Are all amino acids pruned in that first step? And if not, which ones are kept? I think there is a suggestion to maybe keep those that make crucial hydrogen bonds.
That's another good question. So by default, only binding site residues with solvent-exposed area higher than a set threshold are pruned to alanine in the part 1 stage. So not all of them are mutated, but there's an option that user can set it to force to prune all the residues in the active site for sure. And from the question, like, if there's some residues that they want to keep in the pruned receptor, we allow the option to the users so that they can input the manually pruned receptor in the docking process. So in the future, we want to add the option that user can really input the list of residues that they don't want to prune during the pruning step. But yeah, it's not there yet, but we are working on that for sure.
Okay. So I would have control on, I want to keep these two, then I would be able to set those and do it manually for now.
Right.
Okay. Another question here on the IFP score. For the IFP score, how did you combine the scoring metrics? Were the weights optimized?
Yeah, so for now, the metrics are equally weighted, meaning that we haven't optimized the scoring function yet. But yes, we want to do that in the future, and we're expecting to see a better success rate when we use the optimized scoring function for sure. And also the parameters, the weights on each metrics are tunable parameters in the Orion page. So user can really modify the weights in the meantime.
Okay, that's an option we have. Next one here on results. What is the POSIT success rate for the IFP validation set? You show that POSIT works poorly in a low TC Tanimoto combo regime, I guess. How well does IFP work in the same regime?
That's a good question. So we compared our IFP to the standard docking POSIT here on the validation set that I showed in this presentation. And we could see around a 20% increase in success rate in post-prediction, and especially for the area where we saw the low Tanimoto combo score with the template ligand.
So we are able to rescue some of those by applying the IFP method,
Yes,
where the ligands are not similar enough to run POSIT because it needs a
right.
certain amount of similarity.
Yes, that's what we observed from the validation set.
Right. That I think is what we hoped for, and it seems to work.
I guess so.
Question for future plans, I guess. What adaptive sampling in step 2 specifically have you considered?
So we've been working with enhanced sampling group at OpenEye to see whether we can use the parallel tempering method specifically, and also other enhanced sampling methods to see whether we can see more faster and efficient active site residue reorganization for the cases where we saw where we found that the short trajectory MD wasn't enough. So the first thing that we've been working on is the parallel tempering method.
Excellent. Looking at the time, I think these are all the questions we can take for now. We'll answer anything that came in by through the Q&A. Anything else we didn't answer yet by email and follow up. So thanks everybody for attending. Jesus, thank you very much for a really nice talk.
Yes.
And looking forward to our next webinar. Thank you, everyone.